the official title was actually not theory and AI. So yes, this is the recent paper on which much of the talk is based, but I'll actually put it in much broader context in ways which illustrating ways in which not theory can benefit from AI. And actually what's maybe slightly less trivial is the other way around, how AI can benefit from not theory. Before I jump into the talk, I actually want to thank Colin and other organizers for putting this together. I tremendously enjoy this large event, and I do have a little bit of an idea how much work went into planning it. So I think it's great, and it feels amazing, especially at times where I think unifying community is definitely could be a good thing. I won't assume any prior knowledge with artificial intelligence developments these days or machine learning. So there could be several benefits of this talk besides describing how we users in not theory can benefit from it. I also hope to give a gentle introduction or at least a sense of what AI or ML feels like, what it's like to work with it on a daily basis. And of course, like we already mentioned, in the end, I'm happy to give more details, answer questions, and so on. So artificial intelligence is a very large field. It's been in existence for many decades, and it includes many areas. Some of them are kind of esoteric, a little bit philosophical, such as cognition and reasoning. And I always thought that I'll never venture into these areas. I'm very hands-on and like concrete examples. But surprisingly, recent developments or kind of questions that I've been thinking about led me to this questions about reasoning, in particular mathematical reasoning, that became very important for development of AI these days. At a very practical level, to start again with our firmly rooted in concrete problems, we'll discuss machine learning. So this is subfield of AI. And in particular, within machine learning, there are three broad categories. So they're usually described as supervised learning. This is trying to understand labeled data and find best function that fits the data. Think about it as analog of or fancy version of Mathematica's find fit. Then next, slightly more interesting area is unsupervised learning. This is where you have unlabeled data and want to find some structure. Various clustering algorithms or methods and TSNE and so on are part of this field. And this is actually good for trying to make predictions when you have data, but you don't know what to do with that or what it's supposed to represent. And third area is actually where the focus of this talk is going to be mostly. That's called reinforcement learning. So here, the way I described it in the slide is it's kind of area that is all about playing games. So that's what makes it fun, of course, and mathematics is fun. But on a more serious note, reinforcement learning is essentially teaching machines by interacting with environment how to make decisions. What steps to make in the long term, in the short term, and of course, all of the areas that we see around us, such as self-driving cars or planning routes and so on, are all about reinforcement learning because we're basically trying to plan next steps. And many news that we see in the media, for example, how AI plays board games, or in this case, simple Atari games, is also reinforcement learning. So this is the name of the field that we see a lot around us, and that's the field that will be really critical to subject of this talk. So one good thing to keep in mind when dealing with reinforcement learning is to try to do a very rough back of the envelope estimate of how complex is the search space. So reinforcement learning is mostly about finding something, namely, let's say, sequence of steps that achieve a certain goal. If you want to go from Los Angeles to Washington, D.C., we have to find the best route. And good question to keep in mind is how hard is my problem? And this is going to be really critical to many things I'll talk about. So this slide illustrates, for example, that in some cases, the problem is easy, such as for a cat to reach the milk is much easier than navigate a three-dimensional version of a maze. And what it illustrates is that you have to think about how many different dimensions or types of actions you can make at every given step, and also how long is the search path, and also how many possible solutions are there. So when we deal with real world problems, we sometimes have billions or millions of steps to make, different choices of steps. And the good question is to keep in mind, again, as back of the envelope estimate, how does my problem scale with different parameters? For example, when we talk about knots, it's going to be important to us, how does it scale with, say, number of crossings? And this is another illustration of, again, this general idea that I'm trying to ask. For instance, for all of you, hopefully it's easy to see how many possible paths are there for a mouse to go from A to B, from start to finish, if it's allowed to make only two moves, to go down or go to the right. So if I ask you, how does it scale with n, hopefully everybody has an answer. That's a very simple high school problem. But then one can consider variants, such as asking a three-dimensional version of the problem. Suppose mouse has to go from A to B across the large diagonal of the three-dimensional cube, or maybe d-dimensional cube. Important question is, again, how does it scale with n, the size of the cube or hypercube? And these are kind of calculations that in computer science we usually do before we even start working on a problem. We want to have a quick estimate of what are we dealing with, how hard it is, what's the search space. So in this talk, we'll play a lot of games. That's, again, synonymous to saying that we'll do reinforcement learning. And as I proceed through the talk, I'll make my goals more specific. And this is the slide of trying to emphasize what kind of things we'll be dealing with. I won't be interested in solving easy math problems. So high school level math or Olympiad level math, even IMO level math is what I consider relatively easy. And I'll differentiate this from high level research math problems where something qualitatively different happens. So explaining what this qualitative difference is in some sense the main goal of this talk. In other words, what differentiates for us human and also for AI systems solving, let's say, IMO level problems from high level research problems that we don't know how to solve. In other words, the problem remains open for some number of years. So very briefly, I can say more about it. In fact, a couple of years ago, I started working with one of the Silicon Valley companies on accomplishing precisely this goal on the slide, namely winning AI IMO challenge. And one of the reasons I can see this happening really soon, and again, I can't tell you exactly what we're doing because it's protected by NDAs, but without conveying any secrets, I can say that it's clear that we have many problem sets, many study guides. And when I myself was on IMO team and later in my life trained IMO teams, it was very easy to follow solving lots of problems, follow study guides, and within a short period of time, typically 6 to 10 months, get to the level where a student, or in this case, AI system can perform at the level of gold medalist. So this is something that many people can do, and machines also are learning. And again, it's a very achievable goal. But what I want to ask later in the talk is what it takes to try to solve problems where we don't have that many templates, where we don't have that many examples, unlike IMO, where we don't know even a single solution, let alone many problems of that type and how to solve them. So that's going to be qualitative difference. So these are some of the examples. And recently, I started working with David Eisenbud and other collaborators on a so-called algebraic version of the Hertz conjecture. So Hertz conjecture is about diameters of d-dimensional polytopes, and this has been solved by Santos about 10 years ago. But there is an algebraic version of this, which is a search for particular types of linear ideals. One can define a notion of diameter by associating generators of the monomial ideal to vertices, and in that way, monomial ideal represents also a polytope, and one can ask about relation of its diameter to number of generators. And in this algebraic framework, the question is A, interesting, and B, open. So that's one kind of problem from commutative algebra that we've been exploring. Another one, slightly closer to especially low-dimensional topology, is Kazhdan property Tt. Property T is originally rooted as a question in group theory and analytic group theory as a property of a unitary dual, but it can be translated thanks to fairly recent work of Azawa to a search of a path on group algebra. And this element or path on a group algebra then will, if it satisfies certain property, the group has property T. If it doesn't, it doesn't. And one thing I want to emphasize is that both of these problems are research level problems. They may not necessarily be as a high level as Riemann hypothesis, but in both cases, the question can be formulated as a search of a certain property or path or a certain instance. And as I go throughout the talk, I want to start pointing out that many problems in mathematics can be formulated as a search of path, as a search of instance. And this is ideal for reinforcement learning, namely AI systems whose goal is to search for things. As we try to solve different problems, in my opinion, it's a good idea to, especially if you try AI tools, to close some of the long-standing goals. So in mathematics, we value addressing, not only developing new methods, but also addressing long-standing problems, long-standing questions. So in particular, as we work on interaction of AI with mathematics, in my group, we try to ask, how can we maximize this metric, namely the number of years the problem has remained open? I'm not sure if this is the most objective way of describing problems that are hard or interesting. If any of you have other ideas for how to measure hardness or level of interest toward a given problem, we can talk about it. But I think it does represent very roughly the criterion we want to accomplish, because if problem has remained open for a large number of years and it's fairly well known in the math community, then it means that large number of people have tried it, and if they didn't succeed over many years, then that makes a problem hard. But I'll come back to hardness in the end of the talk, and actually this is something that interaction with AI brings to the forefront, namely there will be a need for progress and also feedback from AI of what hardness is in cases where we actually mathematically didn't even think about this question. And some of the problems illustrated here, I'll come back to them. Of course, a dream is that we'll reach something like Hodge conjecture or Riemann hypothesis one day. But again, with this slide, I just want to illustrate if we try to work toward maximizing this metric, perhaps it will happen at some point. And from computer science point of view, the upshot of the talk is that it will naturally lead us to think about very rare events with disproportionate impact. And if this upshot is already clear to you, then it means you probably don't need the rest of the talk, or I should have prepared something differently. But this is going to be basically the goal to explain why solving hard problems in computer science for reinforcement learning is precisely the problem of identifying so-called black swans. These are, again, rare events with very disproportionate impact. Okay, to finish off the motivation or introduction, I also want to point out that working as a mathematician versus working with AI on math is quite different. When I give colloquium talks, I usually joke that if you pay me twice my salary, I probably won't work as much harder than I'm already working. And if you pay me 10 times my salary, the good chances that I'll work actually less because I'll probably collect my first paycheck and then just retire. But so in other words, there is truth in this joke that higher compensation does not necessarily translate to better performance. But with machine learning and AI, it actually does. And one interesting thing is that if you have 10 or 100 times the resources you have, you can actually measure how your performance scales with this amount of resources. In our academic setting, we don't have that much, but we always measure the scaling curves, and everything we produce has the flavor of our job is basically to demonstrate a performance on small number of GPUs. So we don't burn water or make a carbon footprint that harms our planet. But we do aim to produce new algorithms and new hacks that improve the performance of existing AI systems, achieve some success mathematically, and then we also point out that ability to scale the systems allows to unlock further and further problems in math. So it basically gives us not only solution to a given problem, but usually indicates the path of solving the entire family. For example, in terms of crossings, one of the outcomes will be that at some number of GPUs, we can typically a small number, we can solve problems that involve, say, 100 crossings. I'll give you examples later. But what it means is that if you have 1,000 GPUs, then you can solve problems that involve maybe millions of crossings. And this kind of scaling curves is exactly what comes out of the analysis. So speaking of number of crossings, what brought me to this area is precisely this kind of scaling or new, basically new tool that AI offers. Before, my work was in quantum topology, and I'm still working in this area. I'm still thinking about categorification of knot and three-manifold invariants. And the challenge I faced is that many quantum topologists like myself can do calculations in the range of roughly up to 20 crossings. Whereas many interesting problems, interesting from low-dimensional topology perspective, about concordance group, about the homology cobordism in 3 dimensions, and so on, smooth structures on 4 manifolds, they involve interesting Kirby diagrams or knots, for that matter, that have order of 100 crossings or more. So in other words, there was a need before I started working on AI to develop new tools or find new approaches to deal with highly complex knots or Kirby diagrams. And this is what brought me to this subject. My first project, and I'll tell you a little bit about it, was basically to try myself in this field and hopefully convince that I don't need to learn machine learning or AI. But I proved myself wrong. So I learned that I can do a lot more using these AI systems as a fancy modern version of a pocket calculator. It's very helpful. So in other words, I could perform even as a single person with 1 GPU at much better level as a single person without GPU. So that was my lesson back in the day. And I also want to point out, I think it's going to be obvious to many of you, because this is not theory Congress, that complexity scales exponentially with number of crossings. And so is computation of quantum invariants, at least most of them. So if you want to compute Color-Jones polynomials or Color-Humphrey polynomials, then we typically have to sum over states, kind of in a state sum version for each crossing. And as a result, the complexity of this computation grows as n to the number of crossings, where n is the order of the sum that we have to perform. So therefore, if we try to approach the problem via traditional computers, we basically have the Moore's law that says that performance of usual computers improve by a factor of 2 every couple of years. And we also have this exponential complexity of the computation. So what it means is that we're plotting one exponential curve against another, or on a log scale, one log linear dependence against another. And it means that complexity of computation that's achievable with current machines grows only linearly with number of crossings and number of years. And if I need to bridge this gap of 100 crossings, I probably have to wait 100 years according to Moore's law, and I don't have that time. So that's another reason why I personally am interested in new techniques. So current interactions of AI with mathematics fall roughly in this several categories which interact well with one another. Even before AI came to the scene, we had proof assistants. Now one can imagine AI-assisted proof assistants. Developments of AI algorithms is highly aided by mathematical techniques. Topology, representation theory play a role in developing AI algorithms. And of course, one can also view this bridge the other way around, using AI or machine learning for mathematical problems. So this is how I came to this field. But all of these areas interact very closely, and I hope you can see it in this talk. Something I didn't mention until so far, this point about proof assistance, so let me quickly illustrate it. So this is what it looks like. There are many languages in which you can code formal, so-called formal proof of a theorem. And by now, languages like Lean, Isabelle, Cog, and others are very popular. So this is an example of Lean, where some of the simple theorems are formalized. And as you can see, for simple theorems, this challenge is basically finding a sequence of steps, in this case, proof steps, that go from hypothesis of the statement to the goal that we're trying to prove. And this consists of roughly, I don't know, 30 or so steps. That's a typical theorem that's now being formalized, especially with AI. This is roughly the state of affairs. Once we move on to more serious problems, such as Riemann hypothesis, we don't know how long is the proof, but if it exists, it's probably much longer than 30 steps. It's likely to be 1,000 steps or maybe even millions of steps. So that's, again, interacting with the point I mentioned earlier, that harder problems, they'll involve much longer sequences of steps. So that's point I want to make about proof assistance, especially when we think about how AI can aid such tools. And one fun story from formalization is that, of course, the community started with basics and first started formalizing very simple theorems, including Euclid's elements and upward. And I myself, when I first heard about this formalization, I thought, well, it's very good effort, but how many mistakes we're gonna find? Well, interestingly, even in Euclid's elements, the typical proof that we publish in textbooks was found to be not quite correct, because sometimes it happens in math that there are several cases which look similar, and we usually say, well, we're gonna prove one case, but the others are analogous. And this is okay if they're truly analogous, truly similar. But in this case, what happened is that some point, intersection point, was inside versus outside the circle, for example, or the triangle. And these two cases were not really similar, and this occurs once in a while. And recently, in my own research, I came across a theorem that has been published, or statement that has been published for decades, but there was a mistake, unfortunately. And I now have a lot more respect for this branch of development. But for our sake, the point I want to make is that many of these problems, whether we are trying to prove a theorem, find an instance, a counterexample, or an example of something, they look very similar, because they look like navigating or finding a path from A to B such that it meets certain criteria. So in the case of Riemann hypothesis, it would be, for example, finding a sequence of lean steps or cog steps that take us from hypothesis to the goal. So let's play some games. And as promised, many of my examples will be rooted in knot theory and low-dimensional topology. So one simple game can be train AI system to recognize whether complicated knotted diagram, this one is very simple, it only has 10 crossings, but imagine a 100 crossing version of it, is unknot or not. So that's a very simple question, and it can be easily formulated as a game because we know that there are three basic types of moves that we can make, namely Rademeister moves, and one can think of them as sort of movements of joystick in Atari games. So before even trying, you might imagine that this should not be a hard game because there are, again, in the beginning, I encourage you to think about how big is the action space, how many actions one can make. And in this case, the action space is pretty small, so it shouldn't be even probably a board game like chess or Go. It maybe should be compared, this unknotting game should be compared to Atari games. And in the rest of the talk, I'll give you 3 examples of this type of problem. One is literally this decision problem, trying to train a RL system, deciding whether diagram is knotted or not. So here is a more complex version of knotted tangle looking object. Closely related version is training AI system to answer a question whether a knot is ribbon or slice. It's actually a close cousin of knottedness because to 3 Rademeister moves, we can add one more action, namely the bend addition. So in 4-dimensional space, it basically creates a critical point in the surface that's providing, for example, the slice surface for the knot. And there is another version of the question in combinatorial group theory, the Andrews-Curtis conjecture, that has also 3 basic moves and is asking for similar operations, finding a path between initial state and a final state via a sequence of very basic moves, pretty much like 3 Rademeister moves, or maybe 4 if you include this license. So I'll give you some lessons we learned through this work on these different problems that initially I thought would be very similar, again, because their basic steps are extremely similar. And everything we do is, first of all, open source. So here I mentioned GitHub pages, so you can go and download the code and play with it and make experiments on 40 crossing, 60 crossing knots, or whatever your favorite examples are, improve them and so on. So I'm very much an advocate for A, open source, and B, everything we do is on a very small scale, in a sense that we demonstrate performance already on small number of GPUs without leaving any carbon footprint. So here is a lesson, one of the lessons or results from the unknotting game. So this is typical plot that you usually see in computer science journals, and this was our result that as we train reinforcement learning agent, its performance quickly improves as it interacts with environment, and it goes quite close to 100%. If we continue this curve, it will be infinitesimally close. So this was one of my very first projects, and I was super happy about it because this is typical result we want to see. But these days, the question I ask is, it's good, it's great, but what this curve really shows is that performance of recognizing and making the right steps, untangling this complicated knots is great on average. But the right question to ask, and we didn't actually ask it back in the day, is in this epsilon, 0, if you continue this curve, it's going to be 0.001% that are not solved, or that this reinforcement learning agent cannot untangle. Is this something that's consistently not solved, or just on average? And this is an important question, because if there is some class of knots that are consistently, or unknotted diagrams, sorry, unknot diagrams that are not untangled, it means that there are intrinsically hard unknots. And I'll come back to it later. This is another lesson from the same study, which is of slightly different flavor. It's a different second lesson, that it's a good thing to try different AI systems. And these are some of the typical ones. These are so-called off-the-shelf reinforcement learning algorithms, TRPO, A3C, and RW stands for random walker, which is just making steps in random. And as you can see, making random steps and trying to untangle a diagram of unknot does not do so well. Its performance goes down very quickly. Braid length is roughly number of crossings. We were working with braid representations of the unknot diagrams. But then something interesting is in the upper part of the picture. So what it shows is that one of the systems or algorithms, namely this A3C, this stands for asynchronous advantage actor critic. If somebody asks me what it does, I can explain the details, but it's something off the shelf. It's like Honda Civic in RL systems. And it actually does quite well up to a point, but then goes down. But another guy, this is trust region policy optimization algorithm, does really well. And back in the day, when we did the study, we were actually quite happy because we found among several off-the-shelf algorithms one which works really well. In fact, you can see its performance stays very close to 100% and even goes up if you increase the braid length, which is quite amazing. I don't know if we have good explanation for this, but we were very happy. Now, another way to look at this plot is to ask the following question. In the space of all possible algorithms, what are the chances that any of, let's say, a dozen, there is about a dozen off-the-shelf algorithms, is optimal for my mathematical problem? The chances are zero. And this plot very well illustrates it. It illustrates that if I pick an off-the-shelf algorithm, one performs well, one doesn't. But if I take only 10, which are off the shelf and developed for general purposes, that the chances that any of these 10 are ideal for my mathematical problem are actually zero. So what it tells me is that we need to develop our own algorithms if we really want to do better on mathematical problems, especially hard ones. And that's where I'm going to get a bit later. So in the case of studying ribbonness of knots, namely by adding this additional move to the action space of band addition, we also achieved reasonable success, but not that great. For example, here with number of crossings, the performance reaches about 50% at roughly 50 crossings, and then continues to go down. So I don't think we were it was great. It was still better than what we can do by hand. For example, compared to Conway knot, which has only 11 crossings, this is much higher number of crossings. But again, you can ask same question. Other knots which are consistently hard for ribbonness, or every knot is a good representative of average hardness of finding ribbonness. I mean, assuming it's a ribbon, for example. One can ask analogous question for identifying the slice genus. As an application of this code that, again, I shared with you on earlier slides, and I can make slides easily available. I think this is also recorded. You can play with it yourself. One application is to study torsion in concordance group. For example, you can go through all kinds of knots and see if this system does not find them to be ribbon, but iterated connected sum of them is a ribbon, then these are candidates for 2 torsion, and one can try to seek 3 torsion or 4 torsion using this method. So I want to move on to Andrews-Curtis conjecture, which is roughly algebraic version of the problems I described. And I want to thank Anna Belikova for suggesting us to go in this direction, because it turned out to be very promising and insightful for analyzing many questions that are raised until so far. And the formulation of Andrews-Curtis conjecture is basically to see if one can relate presentation of a trivial group with equal number of generators and relations to the most basic one using a sequence of steps, which in very precise sense represent essentially Kirby moves. So for this reason, there are many connections between Andrews-Curtis conjecture and low-dimensional topology, but it can be viewed just as a group theoretic question. And there are two versions of this question, ones which include the three basic moves and the stabilization moves, which allows to change the number of generators and relations by one, is called stable version of Andrews-Curtis conjecture, and both are equally interesting. So here, the length of the presentation is an actual counterpart of number of crossings or complexity. So for example, in this family, which is due to Agbulut-Kirby, there are only two generators and only two relations. And the total length of the presentation here, this family is labeled by integer n, is n plus 1 plus n plus 6. In other words, 2n plus 7. And everything up to length 13 is classified, and all potential counterexamples are ruled out. But there are many infinite families, such as this one, for larger number of, it's tempting to say crossings, but the length of the presentation. That's the right kind of counterpart. So I already mentioned that there are many potential counterexamples, in fact, coming from topology, because these two subjects interact very closely. If you think about generators as one handles and relators as two handles, then this naturally represents something that's homotopy sphere, in the sense that pi1 is trivial. But the question is it real sphere or not? And for this reason, every potential counterexample to Andrews-Curtis could be also viewed as potential counterexample to smooth Poincare conjecture in dimension 4. This is the history of the subject. In the beginning, I said that it's good to optimize or maximize the length of time that the problem has been open. And some of the famous families of counterexamples are Agbulut-Kirby that I mentioned, labeled by n. Miller-Shoup series is also larger class that has analog of this parameter n that roughly labels complexity. And then there have been some more recent works. So here I mentioned, for example, this paper of Mesnikov et al. That has been relevant to us. And most recent landmark, that's the paper I'm talking about, is from last year, where we tried to close some of these potential counterexamples through reinforcement learning and had pretty good success. So I'll tell you a little bit more about reinforcement learning agent that we trained and managed to help us in this study. So among collaborators, I should thank AI system. And what it found is the following, that the distribution of hardness was very non-uniform. So this is an illustration of how length of the path of steps, Andrews-Curtis steps, that solves a given presentation varies as you vary the original length of the presentation or increase in the length, or this number n that labels Agbulut-Kirby, or equivalently, there is a similar thing in Miller-Shoup series. And what you see is that there is a bulk which behaves in a similar way. For example, here, the length of the AC path stays within the same range of, let's say, 50 to 100 steps, but then it shoots off for a couple of outliers. So this is one interesting feature. And this is maybe not such a surprise, especially in this field, but in the case of finding ribbons, analogous plot would be a surprise because the study has not been done. But here, there is a precursor. So in the context of Andrews-Curtis conjecture, we actually do know, thanks to Brinston and others, that there are particular presentations which we do know can be reduced to the trivial one. But mathematically, there is a lower bound on the number of steps one has to make, which is super exponential in the length of original presentation. For example, this one, which is an actual example from the paper and basically feeds on two lines, requires 10 to the 10,000 steps. So its length is 1 and 10,000 zeros. Okay. So think about it. It's much larger than Google. It's much larger than number of steps you would make in a game of chess. The longest game of chess recorded in professional history has 269 steps. A typical game of chess is only 30 steps or 40 steps. So not only games of chess are extremely short, the variance of median and longest is also very small. So this is very different from these kinds of problems where we have to make thousands and millions of steps. So what we had to do in the paper is to develop new AI algorithms and improve existing off-the-shelf RL systems to overcome this challenge. And we're still working on developing other tools like this. And very roughly, it consists of two improvements. One is that you have to aggregate basic steps into chunks, which we can call super moves. And this is clearly necessary if we ever to overcome this super exponential length of the solution. So in theorem proving, this can be viewed as analog of constructing lemmas if you're trying to prove hard theorems along the way, or closing sub-goals in a big goal. But what's more important is that introduction of the super moves has to be done in a dynamic or adaptive way, and this is where the devil is. And what we advocate in the paper is that one should do it based on notion of hardness of each individual presentation, which is also learned along the way. So basically job of RL system or bigger system should be to identify the notion of hardness, and then the super moves that should be added or lemmas should basically be chosen from new successes, from new stages of closing really valuable goals, which in the measure of hardness, for example, the length of the path, are maximized. So here, the red ones would be illustrating that. So therefore, in this work, and in a few days, we'll submit a revised version with more results and more details. So I encourage you to wait a couple of days and check out the new version. We'll present analysis of this hardness, and actually some of it is already in the first version of the study. In particular, one can approach it. There are many, many ways one can approach it, so I'll be very brief about it. And one is to study structure of the AC graph. One can try to draw analogous graph for unknotting problem and for ribbonness and sliceness. In this case, each vertex would represent the presentation of a trivial group. Each edge would be present when two presentations are connected by Andrews-Curtis move, or Nielsen move, as it's sometimes called. And one can ask, what is the structure of this graph? So if you look at neighborhoods of vertices of radius 5 or so, first of all, you'll be very surprised in a number of ways. The distribution of sizes of these neighborhoods is not uniform at all. It's not even Gaussian. It fits in a very narrow band between roughly 70,000 to 90,000. And majority of the sizes it's highly skewed distribution. So majority of the sizes is near the upper limit of this band. So it's extremely non-uniform. It's extremely non-Gaussian. It's not a traditional distribution. It's not a discretization of any smooth distribution you would think of. Also, if you ask about cases that are solved or not solved by RL agent at each step, you would notice that vertices in this AC graph have different properties. Namely, their sizes are actually different. So, for example, everything unsolved fits, or majority of unsolved fits in these narrow bands in this distribution of sizes, which can serve, therefore, as a good predictor what's hard and what's easy. And again, remember, this is important for us in this RL algorithm to learn hardness so that we can start adding the super moves in a way that is informed by what's easy and what's difficult. So this has to be learned in a dynamical way. Okay. So the goal in the end, and the ultimate judge in the end, of course, is mathematics. So question is, what math results have we achieved? What can we show? So there's a couple of theorems which come out of this study. In the case of this Agbulut-Kirby family, until so far, each presentation for n greater than 3 or 3 and greater was of length 2n plus 7. So we did this calculation before, and it was not known how to reduce it to anything smaller. So we managed in this entire family to find path which reduces to n plus 11. And again, we should thank AI collaborator for helping us with this achievement. Bunch of Miller-Shoup series has been solved, including some of the general statements like in this theorem, for example, or these are particular interesting cases that are relevant to us. And here I want to point to a very large number of steps that we had to make. Already mentioned that typical game of chess that AlphaZero plays or game of Go is 30 steps, 40 steps, maybe a couple of hundred. But here on a single GPU, we didn't use any sophisticated tools. We had to develop a system which can easily do 1,000 steps and more. And if we have larger resources, clearly we can scale this much further. I can tell you about scaling curves. So this is an example of result that comes of this study. And I want to finish with advertisement that recently at Caltech, we launched a center initiative on mathematics and AI. And if anyone you know or any of you are interested in joining this effort or collaborating, please write to me, or if you think there are people who might be interested in applying for jobs. This is an instance where AI creates jobs. Please let them know. And of course, thank you for your attention. I'll be glad to answer questions.
Great. Thank you very much. That's great. Thank you. Very interesting. Okay, so why don't we